Today on the science and technology cargo headed to the International Space Station aboard Orbital Science's Cygnus cargo spacecraft. Orbital's Antares rocket is scheduled to lift off Sunday at 12:52 p.m. Eastern Time from the Mid-Atlantic Regional Spaceport's Launchpad 0A here at NASA's Wallops Flight Facility in Virginia. To talk a little bit about the investigations that will expand the research capabilities of the space station crew, are Kurt Costello, Assistant International Space Station Program Scientist, Jeff Goldstein, Student Space Flight Experiments Program Principal Investigator, Robbie Shingler, co-founder of Planet Labs, and joining us by video from NASA's Ames Research Center in California, Mark Murbach, who's the Principal Investigator for TechEdSat 4. For those of you joining us through TV or the web today, we'll be taking questions through social media. You can get those questions to us using the hashtag AskNASA. And we'll start with a few opening remarks. Kurt, would you like to start?
Okay.
Thank you, Rachel. Tomorrow is really an exciting day for us on board Space Station. It marks a milestone event in our operations on board. It marks the 5,000th day of continuous crewed operations on board the space station. And in those 5,000 days, not only have we managed to assemble this unique laboratory that we have, but we've been able to conduct 1,600 experiments to date. And that involves over 1,500 scientific researchers that we've had involved in the program from 82 countries. So really, it's an amazing feat to be able to already have completed so much science. The truth of the matter is, though, with station assembly complete, just finishing up two or 3 years ago, we are now into the period where utilization is really the prime goal of the space station activities, and we have more wonderful discoveries to come. So on board the space station, we do science in a number of different fields. We do science in human research, in physical sciences and biological life sciences. We perform technology demonstration and development. We participate in Earth observation sciences and also educational sciences. Today, we'll talk about the payloads on board the Orb-2 and the Cygnus module. We have over 350 kilograms of science going to the station with this mission, and it covers areas in all of those fields that I just talked about. We'll be talking to some of the experts and the payload developers and principal investigators for those, and we'll also be sharing some examples from the other fields. For instance, in human research, we are flying equipment to help with the force shoes investigation. Force shoes is an investigation that helps us determine the forces on astronauts' muscles and bones as they work out. And this will help us in the end to determine the right prescription of exercise and dietary needs for the astronaut to maintain their bones and muscles on orbit. We also have tech demos flying to the space station in the field of intervehicular activity clothing studies. We're testing new types of clothing for the astronauts that are more resistant to bacterial and odor buildup. That will allow the astronauts to exercise and require fewer clothing changes overall. So we're testing that out. The Cygnus mission itself brings to the station this time payloads that are particularly useful in the technology demonstration category and also in the commercial and educational categories. And we have some of the experts here. We have over 32 CubeSats launching on this mission, and those CubeSats include 28 from the Dove Flock 1B and 4 additional CubeSats, which include microwave radar satellite that will be placed into orbit and take pictures of storms, tropical weather events, and so forth. We also have a number of NanoRacks cube modules going on board, and those modules contain many student experiments. Some of those student experiments are hailing from the great state of Hawaii and the Girl Scout troop in Hawaii. They are testing the capability to grow arugula plants in 0G. Many other of the NanoRacks experiments come from the National Center for Earth and Space Sciences Education. And, sorry, Jeff will talk more about that. Thank you.
Well, I'm here to talk about the 7th flight opportunity for the Student Spaceflight Experiments Program, or SSEP. It's mission 5 to the International Space Station, and we've got 15 student experiments launching on Orb-2, hopefully on Sunday. Thought I would give you a very quick overview of the program and what its goals might be. We launched this program back in 2010, so it's only 4 years old. It is done in conjunction in strategic partnership with NanoRacks, which is our launch services provider. And NanoRacks works with NASA through a Space Act agreement to fly commercial payloads. We're also working in concert with the Center for the Advancement of Science in Space, or CASIS, which is the nonprofit that oversees the U.S. National Lab on ISS. When we designed this program, the idea was to provide a community at the local level the ability to immerse hundreds of students in every facet of real research, to see research for themselves. So it's absolutely authentic. And a typical community has a school district engaged through an implementation plan that has at least 300 students immersed in microgravity experiment design and proposal writing. We typically see 60 to 100 flight experiment proposals from each community. All those proposals go through a formal 2-step proposal review process, and at the Smithsonian we select the flight experiment for each community, so no community is competing with any other. Each community is getting essentially their own real space program. And we've had, I think, 35,200 students engaged since program inception just 4 years ago. Today we are flying the Charlie Brown Mission 5 payload with 15 experiments, and just to give you a sense of that, that represents 15 communities and 6,750 students engaged in experiment design and proposal writing. And from the 1,344 flight experiments submitted by student teams, these 15 were chosen. So just to give you a sense of the overarching range in science that's being undertaken, let me just read from a one sheet that is in the press kit. Efficacy of sprayed enamel coating, onion root cell division, triops as a protein source, microencapsulation in 2 dimensions under microgravity, planarian worm regeneration, penicillium growth rate, mold reproduction rate in microgravity. These are experiments that have been designed by students in grades 5 through 12. And these represent the next generation of America's scientists and engineers. And on Sunday, NASA has asked us to do a short briefing to the media where we've got 5 delegations, 5 student teams here that will present on their experiments. Thank you.
Great. Rachel, thank you very much for having us here today. I also want to thank NASA and the International Space Station Program Office for actually making this possible. And to take a step back, the International Space Station, while it's now in utilization, is really a marvel of mankind. It is one of the most complex systems engineering challenges ever taken. And underutilization, it requires a lot of access to space. And that's why we're here, right, for a cargo resupply mission. So about 15% of the global launch capacity is there to service the International Space Station, to have humans work and live productively in space. And as a result, that gives the ability for there to be reliable access to space. And so we as a company, Planet Labs, are beginning to take advantage of that, to utilize the International Space Station as a platform in order to launch and test future technologies for our spacecraft. So I want to tell you guys a little bit about Planet Labs. And in doing so, I will tell you about our capabilities through Antares, because in fact, we've been on every single launch of the Antares rocket. We were on their first demo launch, the first Cygnus, Orb-1, and then now this one this weekend for Orb-2. So Planet Labs, we're a San Francisco company, and our goal is to image the whole Earth every day. And this is to make the planet visible, actionable, and accessible. And the way in which we do this is by operating the world's largest constellation of imaging satellites to autonomously operate the spacecraft and process the imagery and then put it online for people to get access to it. And so our product is building Earth observation imagery as a service, or imaging on demand, so that we actually understand the state of the world as it is today. So what underpins this is actually building a highly compact, capable imaging spacecraft. And this spacecraft right here was actually an engineering model as part of Flock 1. Internally, we call it Build 7. And on the first chart here, you could actually see an image of our team with Build 4. This was actually one of our first tech demo satellites that went up into space in April of last year. And this went up on the Antares first launch. And you can see the size of our team at that point in time. And the goal of this mission was to see if we can build an ultra-compact, state-of-the-art imaging spacecraft. And on the next slide, you can see in this 6-day mission, we were able to take an image of a forest here in Oregon. So this is first light of Dove 1, which proved the underlying hypothesis of our company that we could build an ultra-compact imaging spacecraft. And that was actually made possible by going up as secondary payloads. Next thing that we had to do was learn how to mass manufacture these spacecraft. So on the next chart, you could see 28 satellites. This is known as Build 7, so this is actually an extra one from that production run. And we wanted to learn if we can mass manufacture these spacecraft, but then launch them into space and operate them. And so I'm going to describe a little bit about what we did with the Flock 1 so that you can understand what's about to happen with Flock 1B. So on the next image, these go up as pressurized cargo on the Cygnus capsule, and they are going up inside the NanoRacks capsules. So 2 of these spacecraft fit inside each one of these sleeves. And here you can see 8 sleeves, or 16 spacecraft, that are mounted on a rack. And the astronauts take out these sleeves and put this on this rack through the Japanese airlock, through the GEM module, and then they attach it to a robotic arm and move the robotic arm away from the International Space Station. Then they release them 2 at a time. And in the next image here, you could see actually what that looks like. So this is a beautiful image. It shows the most complex engineering spacecraft ever built by humanity, the International Space Station, and it's launching some of the world's smallest, most ultra-compact satellites. And this is, we're really grateful for NASA for unbelievable imagery that came from this mission. Ultimately, you don't really get to see your spacecraft once you bolt it to a launch vehicle, and here you get to see a very, very beautiful image. So with Flock 1, we learned how to operate the spacecraft, commission these spacecraft, and get them going. And again, this is the world's largest constellation of imaging spacecraft, and in fact, the largest constellation of spacecraft to be commissioned at once. On the next image here, you can see first light of Flock 1. This is of Davis, California. And then on the next image here, you'll be able to see a sneak preview of first light from Flock 1C. So this went up on a rocket about 2 weeks ago, 11 satellites in a sun-synchronous orbit. And we'll be releasing much more of these imagery as the weeks go on. But in summary, what I wanted to do is with Flock 1B launched on Sunday, we would launch our 71st satellite in 15 months. And that's really quite extraordinary. So that's 71 satellites going through 9 builds of a spacecraft. So every 2 to 3 months, we learn from building spacecraft, putting them in space, and actually testing them in the laboratory of space. And on Monday of this week, we welcomed 3 more people to our team to make up 71 employees. So 71 satellites with 71 employees going up on Sunday. And I'd really like to thank our team to actually really make this possible. We've done an amazing amount taking this from an idea in a garage and actually out into space. So this is agile aerospace. This is, it's about more launches and more satellites, but it's really about getting rich data. Data is our product and to make it actionable and accessible for people. So go Antares and let's go 3 for 3.
Thanks, Robbie. On to you, Mark.
Great. Good afternoon, everybody. It's a real pleasure to be here. I've worked at Wallops for a number of years and I'm very comfortable in the environment over there. It's been very productive. Also, I'm also very appreciative to the ISS program my esteemed colleagues at NanoRacks, who we've worked very close with for the past couple of years, and our co-writers, our rideshare people, Planet Labs, who also were our former, some of which were our former interns from NASA Ames. So if I could have you show the first slide, please. I'd like to talk a little bit about what TechEdSat is. It's a tech education satellite. It's a series of satellites that we've built. We're launching on Sunday is the fourth one in the series, also combined with some suborbital launches from Wallops. So in that satellite, actually, you see we go back 2 years. So our small team, comprised of young professionals and interns from various universities, including San Jose State, University of California, University of Idaho. We got together, and actually in a short time we produced the first 1U CubeSat that was deployed from the space station. And that's what you see on the first slide. About a year later, on the second slide, if you please, you see a 3U satellite, meaning it's 3 times the size, also being jettisoned. And in this case, we were advancing experiments in CubeSat communication and also deorbit techniques that are of particular interest. If I could have you show the third slide, this is now a depiction of what this experiment looks like. So it's a 3U satellite. You see one of the forward antennas, and off the back end is a peculiar-looking object, which is an exobrake, an exoatmospheric drag device that allows us to deorbit fairly rapidly something from an orbital platform. So we did that in TechEdSat 3 and 4, and what we're doing is advancing the techniques such that in the future that we could modulate or change the shape of that drag device such that we can steer the satellite to the top of the atmosphere. Why do we want to do this? If we look at slide number 4, we have a series of reentry. It's a 3-step process by which we would now take a larger device that would also come from the space station carrying valuable samples. This is a sample return concept, in fact. We would go through a deorbit process using a exobrake that we're developing at small scale. And then it would go through a process of having a self-stabilizing hot reentry vehicle that you see in the middle part of the slide. Finally, the terminal reentry you see at the back with a GPS-guided parafoil. So slowly we're practicing all of this. As you can see, we're doing the deorbit stage, and in Idaho and Washington State with our university colleagues, we're developing the GPS-guided parafoil. From NASA Wallops, we've actually flown the TDRV, the self-stabilizing reentry probe. Another application that we're very interested in is then taking the idea of compartmentalizing a small satellite and its electronics and carrying it to another planet. So in slide number 4, you see our Atromos concept. And again, at the left, the upper left, you see our self-stabilizing reentry probe going through a entry, descent, landing sequence, and finally putting a CubeSat-sized device, now in cylindrical format, on the surface of Mars to basically validate atmospheric pressure and actually go to very interesting places at Mars that are otherwise inaccessible. We would do this in a piggyback fashion. So if I could have the camera pointed back toward me, if you don't mind, I will show you, and perhaps many people in the audience have seen this, but what I'm holding right now is was one of our first CubeSat models, in fact a PhoneSat, that perhaps were worked on by 2 or 3 years ago from our colleagues, and now in various different companies in the aerospace industry. So this is what we started with. So this was the first thing cast off the ISS. And over time, then we grew 3 times in size. So this is a 3U CubeSat that's representative of our current payload, also of our companion doves. And so what I have in here is also a small-scale version of a tube-deployed reentry vehicle. So this would come out the back on that previous slide that you saw there, and then the drag device, the heat shield, if you will, is oddly put in the back of the payload, giving it a lot of stability. So perhaps you can see this. And then at the right time, a payload canister would slip out of the back, and this is what we would recover from a orbital platform or perhaps put on the surface of Mars. Its real size and if you'll excuse the noise, it would be something like this. So this is a actual sample canister that we developed for recovering samples from the ISS, and it would be very close to the same size of an object that we would like to place on Mars with the kind of technologies that you see being developed by this current flight. So that, in very short form, is what we're trying to develop. And I'd like to close with one of my favorite quotes from a luminary in the aerospace sciences, and his name was Theodore von Karman. And I like this. I tell this to my students. Scientists study the world as it is. Engineers create the world that has never been. And with that, I'll pass the baton back to our esteemed colleagues at Wallops.
Okay, thanks, Mark. Okay, so we'll take some questions.
Rachel.
We'll start here and have some on the phone as well. As a reminder for those watching from afar, you can send your questions to us through social media using the hashtag AskNASA. And if you will please state your name and affiliation and to whom you're addressing your question, that will help us out a lot. Okay? Go ahead, Ken. Wait for the mic here.
Hi, Ken Kramer, Universe Today. I have a question for the last speaker. Very interesting what you talked about Mars deployments. How close are we to actually sending these satellites to Mars? And talk a little bit more about the missions they could accomplish. Thanks.
Mark, I think that one might be for you.
Oh, I'm sorry. I didn't hear the question quite well. Could you repeat it for me, Rachel?
Go ahead.
It's very interesting what you talked about. How close are you to actually deploying, sending these satellites to Mars, and what kind of missions could you accomplish?
Thank you very much for the question. I think we're targeting a 2018 or 2020. The idea would be that it would be a piggyback mission aboard either a European or American larger mission to Mars. And so we would use excess mass capability and independently re-enter the atmosphere of Mars and land, and for example, mid-latitude regions or in other very interesting regions of Mars that we can't access. So our technology would be ready by a 2018 opportunity or 2020.
Okay, next question.
Thanks. Jeff Faust, Space Review. I think this is for Kurt. As you balance the science experiments that go up to space station, I understand there are probably some that are Dragon specific because they have to come back down. Are there any that are Cygnus specific because of some capabilities of that spacecraft? Or are you able to slip them back and forth as the launch schedules go?
Well, this great question. This probably isn't fair to the TV audience because they didn't see the Cygnus briefing that occurred just before this one. But because Cygnus does destructively re-enter, there are some examples of fire investigations, notably the Sapphire investigation, that make a good fit for the Cygnus vehicle rather than a SpaceX, which is where we tend to try and recover all of the science on board. So there are a certain class of missions, particularly those that have to deal with spacecraft breakup and reentry and upper atmospherics that fit very well to the Cygnus profile, but really wouldn't fit into the return of a SpaceX Dragon.
Okay, other questions here?
It's Ron Maddox. I'm with the social media group, and I was wondering if you could speak to the technology that is used to not only coordinate the cameras, but to also keep them from overlapping and keep them in orbit.
Sure. So the technology that we have inside the spacecraft, and here again is an engineering model from Flock 1 that went up in January and deployed in February. About 2/3 of the volume is a telescope. And then the thing that's sticking out the back is the camera and the associated electronics. And if you think about what you need inside of a spacecraft in order for it to operate, it's very, very similar to the components and the subsystems that you have inside your phone. So you need a radio, you need batteries, you need to recharge those batteries, a computer, fast processor, and a whole bunch of sensors on board like accelerometers and magnetometers in order to sense the environment. But to answer your question specifically around pointing, we use two modes for pointing our spacecraft, one of which is utilizing the Earth's magnetic field. So we have three magnetorquers on board, and what these are is a tightly wound copper coil that if you put a little bit of current through it, it creates a magnetic field. So you have three of these coils on each one of the three axes of the spacecraft, and then operating inside a magnetic field, it pushes off of it, and that's how you get very, very coarse pointing. Then we also have three reaction wheels inside of this, and this is a motor that spins up, again, one on each axis. And this allows for you to then use the conservation of angular momentum in order to get fine pointing. So there's actually a lot of capacity that is built within this really small spacecraft, and the exact same type of subsystems that are necessary inside much larger spacecraft.
Hi, my name is Kelly Gall. I'm with the NASA Social Group and with the American Society for Microbiology. My question's for Dr. Goldstein about the student experiments and what disciplines are represented and what microbiology might be on board.
Well, there's a whole variety of disciplines that are appropriate, and the experiments simply need to be designed to operate within a very simple fluid mixing enclosure, which is a volume that can be divided into three subvolumes. And so microbials work very, very effectively here. If you have a freeze-dried microbial in one volume and a growth medium in a second, an astronaut will unclamp the first clamp and activate the microbial, and at some point the student team will ask the crew to introduce a fixative to kill and preserve the biology so that when it comes back down, this identical experiment done on the ground truth can be compared to the one that flew and see what the impact of a microgravity environment has on that system. So there are quite a few microbials on board right now. Planarian worm regeneration, penicillium growth rate, mold reproduction, lettuce growth, not a microbial but biological system.
Other questions from the audience here? Okay.
Yeah, hi, Bill Harwood, CBS for Robbie again. And I'm sure this is on the website. I just hadn't had time to look for it. What is the average lifetime of one of these guys before drag brings it down? And what's the long-range plan to replenish the constellation as it goes forward?
Yeah, as I mentioned in my opening remarks, with this launch on Sunday, this will be our 6th launch over the last 15 months, and 3 of them have been to a really, really low orbit, so to the International Space Station orbit, and the other 3 are much higher. And so you're right to point out that the limiting factor, especially in a low orbit constellation, is drag. And drag has to do with the ballistic coefficient, but really has to do with the mass of your object and the surface area and the velocity vector direction. So right now we are in a solar max, and therefore the atmosphere has expanded. And so at 400 kilometers, which is on average where the International Space Station is, these satellites last on the order of months. So about 6 months or so, but which is absolutely perfect for us in order to practice, again, what we call agile aerospace, which is to test out new technologies, new operations, and new capabilities, and then feed that into the next generation of our spacecraft that we deploy. For operational constellations for longer term, going up to about 500 kilometers, they would last about 5 years.
Okay, and I think we have one question on social media. You want to take one from the audience? Okay.
Taylor with USA in Space. Just a follow-up to that. You said we're at solar max, and that's decreasing it down to 5 months. How much longer would it last if we weren't at solar max?
That's a very good question. It would probably be about 2 times longer, so on the order of 9 to 18 months.
Okay, now I think we have a couple from social media in the front here.
Wonderful. This first question comes from Twitter user Scott, who asks, how long will the sensors be functional for in collecting data?
For Planet Labs? You believe so? Well, we will find out. We just launched 2 weeks ago to an orbit that will be up there for about 5 years. Right now, they're operating perfectly, but we will see degradation over time in performance. Then take that into consideration as we iterate on our technology moving forward. But for now, the limiting factor has been altitude with respect to build 6 and above.
Wonderful then. The second question comes from Twitter user Dylan, who asks, will it help make the ISS bigger? I believe what they're referring to is the cargo that's being carried up, the science experiments and things like that.
Okay, Dylan, thanks for the question. The cargo would technically make the ISS a little bit heavier, but not bigger. It doesn't technically expand the dimensions of the spacecraft as we know it. Now we will be jettisoning a number of CubeSats, and those will go on to have their own life outside the space station. But we are bringing valuable science to the space station, and that increases the knowledge that all of us can gain back here on Earth, whether that's developing new prescriptions for exercise and healthcare, or whether it's developing new technologies that go into showing how we can commercially utilize low Earth orbit access to space.
And I think we have one on the phone from Frank Mooring with Aviation Week. Frank, are you on?
I'm here. Thank you. Can you hear me?
We can.
This is for Robbie, and it has to do with your operational constellation. At this point, do you know when it will be fully operational, how big that constellation will be, the altitude, and I'm really interested in obsolescence on your spacecraft, how often you expect to upgrade, and what your launch rate will be, if you know those numbers. Thank you.
Yeah, Frank, thanks for the question. We aim to operate our spacecraft around 400 to 600 kilometers. So that's about the altitude at which we'll go for. So it's a useful lifetime of around about 5 years when we get above 500 kilometers. And we have a number of conversations trying to get access to space as secondary payloads over the coming 18 months. But we anticipate that we would be able to launch about once a quarter in order to replenish the constellation, but in addition to that, provide much more robust capability as we get into operations. But the ones in sun-synchronous orbit will be up there for a number of years, and already, Frank, with Flock 1C, we're getting excellent imagery back, and there will be a lot more data coming out on that over the next couple of weeks.
Okay, we have time for a couple more questions from the audience, if there are any. Okay, in the middle here.
Harvey Leifert, freelance writer. I'm just curious as to what's going on the launch pad. Cherry Picker has gone up and is investigating.
It looks like normal pad operations, hopefully. They continue to make progress at the launch pad, so. Other questions? Yep.
My name is Ari Kutsaratis, and I had a question for Robbie again. Those microsatellites, what sort of data rates do they communicate back to Earth with?
That's a great question. So we have seen upwards to about 75 megabits a second with our large ground stations, in addition to what we currently have in models build 9. And that will continue to evolve over time as we add additional power and upgrade additional compression mechanisms on board our radio. But we started with very low speed transmission, UHF transceiver, which is very, very low speed. But now over time with the X-band down, we get quite a bit of data down.
Okay, any last question? Okay, well, we'll go ahead and wrap up. I'd like to thank everyone for joining us today, especially our participants. For awareness, we'll hold a pre-launch status briefing tomorrow at 1 p.m. Eastern from here at Wallops Flight Facility. You can find out more about the space station and the science payloads headed to the space station at www.nasa.gov/station. Thanks very much.